So, last time I talked about this this uncertainty area, which if you prepare your quantum system in a coherent state alpha, which we know in the number basis it can be written as minus alpha square by 2 multiplied by n is equal to 0 to infinity alpha to the power n by n square root of n factorial and 0 sorry n, these are the number states. So, what we have seen is that if I look at the expectation value of this generic quadrature operator, which is a direct lifting of corresponding classical quadrature operator, which is x cosine theta plus p sine theta. Theta is the so you have the quadrature plane, this is x and p, these are the not just operators, and then you take the operator corresponding to this angle theta. So, this corresponds to x theta. Okay. So, here these quadrature operators, as we know, these are written in terms of the annihilation and creation operators a plus a dagger by root 2. This root 2 or 2 or some people do not even take this factor. So, so there is a difference in the literature, and basically it will be reflected in some of the expectation values and also the variances and all that, but I mean I am going to take this thing. Okay. So, that and why and so this is iota a dagger minus a divided by root 2. Okay. And I have, so these are dimensionless quadrature operators, as one can see, and they satisfy these relation I, the commutation relation. Okay. And this is equivalent to this commutation relation, that a and these are operators a and a dagger, this is equal to 1. Okay. So, yeah, so this is a kind of rotated version of these quadrature operator. Okay. Now, if I consider the expectation value of such a quadrature operator with respect to any such coherent state, then this will be, according to this definition, 1 upon root 2 alpha a alpha plus alpha a dagger alpha, right, according to this definition. And this we know that this coherent state is an eigenstate of this annihilation operator A corresponding to eigenvalue alpha. So, as a result, this will be 1 upon root 2, this is alpha, and this you will have to consider the action of. So, this is basically A alpha dagger of that. So, plus, so therefore, this will give you alpha star. Okay. No, sorry. This is just x. So, this is cosine theta plus what will be the other one, I by root 2, what is that, alpha a dagger alpha minus alpha a alpha. So, and this is sine theta. So, this is cosine theta plus I by root 2, this is alpha star minus alpha sine theta. And so, this is your yeah. So, now you can call this thing as this classical quadrature as alpha plus alpha star by root 2 and p, these are not operators, just numbers, these as iota alpha star minus alpha by root 2. So, here you see that this is basically same as the value of the classical quadrature variable. Okay. So, this we mentioned last time, that if I take a coherent state and take the average value of this quadrature, generic quadrature operator, it will correspond to the corresponding classical, it will correspond to the classical value of that operator, right. And what more you can show is that, and this is what you can calculate, is that if I look at the dispersion. So, namely delta of theta square with respect to alpha, and this is nothing but alpha x theta square minus okay. So, if you calculate that, this is I am not going to calculate, you can calculate it, you will see that, I mean for the calculation you will have to use this rule, this formula. Okay. So, if you do that, what you will get to see is that this is equal to half, whatever be the. So, this is for all theta and all alpha. So, theta is the angle and alpha is a complex number. Okay. So, what you can think of is that here is your x and p, the classical quadrature variables. Now, you take the value, so namely this value, this is theta. So, this is the point which corresponds to your x and p, because it has this component x cos theta and p sin theta. Okay. And this value is, this is what which corresponds to the alpha, the complex number alpha, in the sense that you see that alpha is equal to, if you look at there, this is equal to x plus I p by root 2. Okay. I mean from this relation you can get it. So, at this point this is your classical value. This dispersion what you are getting is so basically so this is the dispersion that you are getting. So, it is a kind of circle of radius something like this, I mean half of that So, this is half of alpha delta, you can take it anything because it is independent of theta. Okay. So, you see that classically you have this fixed value, one value, whereas quantum mechanically because of this dispersion with respect to this coherent state, you can have, if you measure in with respect to this coherent state, what you will get is any value here within this. Okay. So, what does it correspond to? So, this is a kind of uncertainty, and this satisfies of course this uncertainty, that delta x square alpha times delta p square alpha, this is equal to, actually all of them are same, this is equal to half is equal to this thing. So, their product will be greater than is equal to 1/4, which is the minimum uncertainty. So, why? So, why you have this kind of uncertainty here, whereas classically you have a fixed value? This uncertainty comes because what you have done from the classical case to the quantum case is that you have lifted these quadrature variables to quadrature operators and which do not commute with each other. Okay. So, at the operator level, because they do not commute, you have this kind of uncertainty. So, this uncertainty is inherent in quantum theory. You cannot reduce the uncertainty below this, okay, below this area. Area is this product of these two, right. Classically, of course, there can be uncertainty in this value, and that uncertainty comes from preparation. I mean, I can have an electric field, for example, which is prepared with some prior probability distribution. So, that is also uncertainty, that is a preparation uncertainty. Here this uncertainty is inherent due to quantum mechanics. Okay. So, if you measure, this is what you will get. I mean, if it is not a coherent state, even more uncertainty will be there. Right. So, this particular circle is called the uncertainty area, and basically important thing is that if you know this uncertainty area, I mean the location of it, then you can identify it with a coherent state, right, because only for coherent states you will have this uncertainty area as a circle or circular disk, whatever you want to call. For no other state it can be of this form. And one more thing is that, you know, if I am not sure about whether it is this coherent state or other coherent states, then what you can have is, so let us say this is my x and p in the quadrature. Let us say my parameter space is such that it allows you know, possible quadrature values in some region like this. Okay. Let us say, I mean this is, so let us say I consider a quantum state of light where the quadrature values, if I calculate, it will fall under this area, let us say. Okay. Now, you can think of, as you know, this I mean uncertainty area, you cannot reduce its area lower than this, that is not possible quantum mechanically. So, what you can think of is, you know, like tiling this area with this uncertainty area. So, for example, maybe like this, there may be some overlap, maybe some non overlapping thing, etcetera, etcetera. Okay. So, it may overlap and may not overlap. Now, if I have a source of light and if I want to send information through that light, okay, what I can do is I can try to figure out in this area, because you know my source of light tells me what is this region, and then what I can do is I can try to identify what is the total number of non overlapping uncertainty areas. Okay. There will be some overlapping, but you look at the non overlapping uncertainty areas. You can now encode information into the coherent states corresponding to those non overlapping uncertainty areas, and that will tell you, because why is it so? Because you know, because the if you have non overlapping uncertainty areas, then you can identify the individual uncertainty areas through the corresponding coherent states, right, and therefore, you can identify the informations also, right. So, this is a way of communicating through quantum state of light. Okay. I mean, how will you encode information through these coherent states, etcetera, that is a separate issue. That is fine, that is okay, that is fine. But you know, encoding information also demands that you should be able to decode it efficiently, right. So, this is one way of doing it. So, if you can figure out the non overlapping uncertainty areas, and then we encode your information through the corresponding coherent states, that will serve the purpose. So, note that here the coherent states, no two coherent states are orthogonal to each other, still this is possible. Why is it possible? As I said, because if you have two non overlapping uncertainty areas, you can identify with each of them a coherent state. I mean, if you consider overlapping, then things will become difficult. Okay. So, this kind of dispersion in literature is called quantum noise. So, this is a noise because you are not identifying a particular point in the phase space, but you have a region of phase space. So, this is called quantum noise, and this noise is inherent, you cannot get rid of that. If you do experiment or whatever on your quantum state of light, what you can do is you will create noise which is more than this in general. So, for theoreticians as well as experimentalists, the goal, one of the important goals is to reduce the noise, to make it as close as possible to quantum noise. Okay, good. So, now I think you have a kind of understanding that when I go for quantum state of light, we will have to introduce this quantum noise. This is inherent, you cannot avoid that, but you will have to live with that. Okay. Sometimes this noise is useful also. And in fact, when we discuss about the channels, quantum channels for like Gaussian channels and on that, those channels will be identified through this noise. Okay. So, let me again go back to this p distribution, because today what I am going to talk about these in details about the p distribution is connection with the normal ordering and all that. So, what we discussed is that if I take a density matrix of my system is a, you can think of it like single mode quantized radiation field or a one dimensional quantum harmonic oscillator. So, I take a density matrix which is basically mixture of projections on pure states. Then because of the over completeness of the coherent state basis, we know that I can write it as 1 upon pi square. This is d square alpha, d square beta, where alpha and beta these are in complex plane. So, this is alpha rho beta, then this is alpha beta, right. This is what we have seen, and we also discussed that this Glauber-Sudarshan P representation tells me that this is nothing but alpha belonging to C d square alpha. You have the diagonal representation P rho alpha alpha star. So, this is a real valued function, then it is alpha alpha. Okay. So, this is what is known as P distribution, in the sense that P rho of alpha alpha star is real, and if you integrate over the complex plane of P rho of alpha alpha star, this is equal to 1. So, it is not true that this is always non-negative, it is real. So, this is why we say that this is a quasi probability distribution function, not exactly probability distribution function. Okay. So, the question is how how does one get from here to here? Okay. So, I will take a roundabout way, okay, um, to discuss about this connection. So, let me start with a normally ordered operator. Normally ordered operator. So, normally ordered operator means you take this operator O n means normally ordered, and any operator for my system will be a function of A and A dagger. I am talking about the single mode system. This is A and A dagger, and what is this? This is n and m is equal to 0 to infinity. Let us say this is C n m, this is coefficient. Normal ordering means all the powers of A dagger will come on the left and all the powers of A will come on the right. Okay. So, this is my normal ordering, and as you know, by using this commutation relation, any operator, any function of A and A dagger, not necessarily normal ordering, can always be cast in this form. Okay. Right. So, now I again take a density matrix and let us take the expectation value trace of rho O n A dagger. Right. So, this will be sum over n and m is equal to 0 to infinity C n m, then this is trace of rho A dagger to the power n A to the power n, correct? Yes. Okay. So, now I put it, now I use a trick here. These are coefficient, just numbers, trace of rho, and now I use this thing delta. This is an operator, delta function operator. So, this is sorry, I will have to use like this, alpha belonging to C d square alpha delta of alpha star minus A dagger times delta of alpha minus A alpha star to the power n. Oh, sorry, this is sorry, this should be like this, alpha star to the power n alpha to the power m. Can I write in this way? I can, right? I mean, now for the timing, do not ask me about these convergence etcetera of this integral, but at least symbolically I can write it. A is an operator. I mean, I should have used hat there, and alpha is a number, scalar. Yes. This is just an operator. You can define it on some state vector. Okay.
Alpha cannot be scalar based. It also has to be operator.
Why? Alpha times identity.
Oh, alpha times identity.
Yes.
But then it will never be equal to A dagger.
What is not ever be equal to A dagger?
A dagger is a off diagonal element.
Yes. Yes.
Alpha will be at
Yeah. So, if I do this integration, what will you get here? This part.
it will get 0 because there will no value of alpha for which it will be equal to A dagger.
Why? You know, what are the eigenvalues of A? These are complex numbers, right. So, when I talk about values, it can take values, right. A can take alpha, A dagger can take alpha star.
Does rho has to be inside? Can rho be inside the
No, I mean this is
integral?
trace. I can take rho inside integral, that is not an issue, because rho is independent of alpha. But does it make sense or not? So, what I am doing is I am replacing this one by this. So, symbolically it is possible. I mean, I am not talking about the these all the mathematical details that.
One way I would imagine this to be possible if alpha was a generic operator, not just alpha times identity, but a matrix for the harmonic oscillator with all its elements, and we are integrating it over.
Yes. So, what you should do?
There is
Yes.
chance that it will become equal.
Yes.
To
So, I'll basically I'll come back to that, but how will you establish that, look, this is equal to this? How will you establish this? What are the possible ways of doing it?
Formally, it will be.
Yeah. So, you will have to take matrix element, because this is an operator. You will have to take matrix element that operator.
And I think in this kind of a step, if the fact that alpha is actually an eigenvalue of A, that
Yes.
helps, because alpha is alpha alpha.
Exactly. Exactly.
So that's how we are able to do this.
Exactly. Exactly. So, you can take again matrix element of this A dagger n A m in terms of some coherent state basis, diagonal matrix element like this one. And that will serve the purpose, for any gamma you can show that that matrix element is same as the matrix element of this, then that is enough.
Because I mean, specifically, I was wondering, like, no, yeah, it's okay. It's okay, it makes sense.
And should there be an alpha bracket there?
No, because this is an operator, okay. This is an operator. I should have used some hat for A and A dagger, but this you assume. I do not use this hat because these are not Hermitian operators. Okay. So, for the time being, so I have written it symbolically, but one can prove it also. Okay, right. So, so what is it that you have here? And now I will have to do some manipulation. So, this is n m is equal to 0 to infinity C n m. Let me call these as P rho of alpha star. I mean, although I have called it as P rho, but I will come back to this. I mean, this is actually the same P rho. Okay. So, times alpha star to the power n, alpha to the power m. And what is P rho in this case? If you are very strict about mathematical symbol, maybe you can put it at prime. Okay. Then I will show that P prime and P are same. Okay. So, this is by definition, this is trace of rho delta alpha star minus A dagger delta alpha minus A, right. So, this is my definition of P rho prime.
So, that last equal to, we need an integral.
Sorry, what?
The last
Sorry, yes. Yeah, I will do this, where shall I do this integral? Maybe I will put it here. I mean, I generally physicists do this thing, interchange the sum, integral, all these things, but we assume that this is true. Okay. Actually, this is true, because all these are bounded, I mean not p rho, but in principle one can do it, right. Okay, good. So, this is your alpha belonging to C d square alpha p rho prime alpha alpha star, and now I call it as O n alpha alpha star. Now, what is your O n alpha alpha star? This is by definition n m is equal to 0 to infinity C n m alpha star to the power n alpha to the power m. Okay. So, if you look at these two expressions, this is an operator and this is a function, just scalar. What is the difference? Replace A by alpha, A dagger by alpha star, that is it. Okay. So, you see that if I want to calculate the expectation value, average value of normally ordered operator with respect to my state rho, it is equivalent to the statistical average of this function, the corresponding classical function you can say, with these quasi probability distribution. So, this is what we do in classical statistical mechanics. Okay. So, this is at the operator level, but this is at the function level. Everything here is a scalar function. Okay. And why this is important? Because in experiment, if you have a normally ordered operator, you can quote unquote perform measurement of that with respect to the state, and this average value will be governed by this average value. Okay. Right. In fact, now we should show that from this function you can figure out rho kind of uniquely. Okay. So, how to do that? Okay.
So, moving from the third line to fourth line, P prime rho is what exactly is it equal to?
This one.
Oh, sorry. And there is a summation. What about the integral over? Okay, it's still there. Integral is still there.
Yes.
Well,
Okay, good. Now, I have to show that your rho is nothing but This is what I need to show. Okay. Right, good. Okay. So, let us do one by one. So, let us take okay. So, let us take this thing. So, trace of this quantity alpha belonging to C d square alpha p prime rho alpha alpha star alpha alpha. This is my rho delta of alpha star, no, not alpha star, what is that I will have to do. This is for rho I am doing this, and then I will take not alpha star, this is let us say beta star minus A dagger delta beta minus A. So, what I am calculating is basically this part, this right hand side part. Okay. So, this will be alpha belonging to C d square alpha p prime rho alpha, oh no. So, what is this I am calculating? Okay, fine, alpha alpha star. Now, I am taking trace. So, this will be alpha delta beta star minus A dagger delta beta minus A alpha. Is that correct? Because I am taking trace. Okay. Now, what is this? This is an operator acting on alpha, and Kate alpha is an eigenstate of A corresponding to eigenvalue alpha. So, therefore, instead of this, what I can write is delta of beta star minus A star delta of beta minus A, and then alpha alpha anyway it will be 1. Is that clear? This quantity is same as this quantity alpha sorry alpha sorry alpha. Is that correct?
So, I have a question. So, in all this calculation, the two delta functions are not redundant in the sense that
No, these are independent operators, independent functions. That is why I am taking p of alpha alpha star. I could have taken just p of alpha, because this is function of two complex variables. Right. So, therefore, if I replace these, what will I get from here? You will get p prime of rho, this is beta beta star. Is that clear? Right. So, yes. So, what you are getting is that if you take this representation of rho, then you are reproducing that result, right. If you take this representation of rho, then actually you are reproducing this result, is not it? What is it that I have done here? Instead of rho, I have taken this part. Right, in that formula, instead of rho, I have taken this one, and what you have obtained from there is this function. Okay. Now, for the timing, forget about this. So, instead of rho I have represented, yes.
I mean, we wrote rho is equal to that, and then we proved.
No, forget about rho is equal to this. So, let us take only these operator.
Yes, but so my question is that seems to be independent of beta, but here we have a beta.
Which is independent of beta?
I mean that equation over there.
No, this is my represent, this is just, this is the operator I have taken here. It has nothing to do with beta here. This is the operator I have taken.
But in the last step we happened to get a beta, like last.
No. See, this is my operator, right? And I am calculating this trace. Here, this is the operator, and this is the trace with respect to this operator. Okay. So, if I calculate this, right, then
We found a trace with respect to that
yes,
operator which has beta.
yes. So, therefore, this is what I am getting. So, from here I should conclude that this is nothing but your rho. Why? Because this, look at this formula, this is where we get, and what I am assuming here, of course, is nothing assumption, this is true, that because this is for any alpha, right. So, therefore, this equality follows from the fact that choose any beta, this trace is equal to this one, and as a result this operator has to be equal to rho. Yes.
I mean, how do I know that this is unique or
Which one is unique?
rho? I mean, we might have substituted some other kind of rho, and we might have got the result.
Yeah. So, which basically it tells you that this distribution function that you will get is unique to rho. Okay. Why? Because this kind of functions, all this is operators, these are not very well behaved operators, they form a kind of basis. Okay. So, it does not matter, I mean, although this is not very well behaved operator, but if you change alpha and take the full set of all those operators, they will form kind of a basis, right. And as a result, if you can express, if you can figure out this function, this is unique to rho. If you change rho, this will also change. So, this idea that this is a one-to-one correspondence with rho depends upon the properties of these operator functions.
So how will we calculate this, let's say for rho thermal state, or let's say ground state,
Yes.
vacuum, pure vacuum state. So what will be function will be for that?
Which one?
How
This
will you
P.
go about calculating this P?
Yes. So, that I will talk about, but here you can directly put the expression for rho.
I mean, if I put just ground state there,
Yes.
see how will I calculate?
Yes. So, then you put the ground state 0 0 delta alpha star minus A dagger delta alpha minus A, right. So, this is what 0 delta alpha star minus A dagger delta alpha minus A 0, right. Now, what is this? This is delta alpha star delta alpha.
How did this step, I mean, this delta function on a scalar times identity minus
No,
A
this what is this one? Well, what is this one? This is delta of alpha, because A acting on 0 give you 0 eigenvalue. So, delta of alpha 0, right.
How did we move to this?
How do you move to this? Okay.
I mean, if it was just alpha minus A,
Yes.
then it will be alpha 0.
Yes.
But
think of it like delta function, you can think of it as a limiting case of a Gaussian function, right. So, it is a limiting case of some Gaussian function of alpha minus a. So, apply that Gaussian function on k at 0.
Another way is like, I mean, if delta is like generic polynomial function in alpha minus alpha a.
Yes, yes,
So
yes,
it will have real third term, linear and quadratic term,
yes,
and then we'll reproduce this value. It will be equal to delta alpha
exactly, exactly,
acting on 0.
yes.
But delta, we know, we are already familiar with delta. Delta function is something.
It is not a well behaved function. I agree.
Oh, you're saying Gaussian. Take it as a Gaussian.
Yes, in
and
the
leave some
limiting
limits.
case. Yes,
Then we can do Taylor expansion.
yes.
Okay.
Like take it like e to the power what is that minus alpha minus a square by factorial 2 by 2 etc., etc., and then apply on 0.
Okay. So then this will be delta alpha star delta alpha.
Yes,
So it will be peaked at 0.
it will peak at 0. Yes, yes. So, this is basically a a delta function at 0.
So, what were you saying about delta function being basis?
So, for all alpha, if you choose these function, these operators, they will form a kind of basis. This is not a well behaved operator basis, but you can express any operator as superposition of these operators. In fact, if you look, yes, yeah,
In terms of delta function, I can write any operators.
yes, you can.
So that's why since we are writing it in terms
So, because alpha is arbitrary, and therefore, if where is that? Yeah. So, this is a kind of unique representation. Yeah, if you look at this one of these papers of Cahill and Glauber, so there they discuss about maybe not exactly about delta function, but what will be the operator basis. Okay. So, there is operator basis corresponding to the displacement operator. You can also think of operator basis in terms of delta functions.
So sir, how will delta alpha minus a act on 1 get 1? What will be its action?
This is right. Okay. So, yeah, so that is why this is not a very good expression. I will have to come up with a different expression for calculating, but in principle you can do that. This is a dagger acting on 0, right.
Yes.
Okay. Now, you will have to use the commutation relation of a and a dagger, so that you can bring this back here. Okay. And then you can apply this on 0. Again, how will you use commutation relation? Take some kind of Gaussian expression for the delta function. Okay.
And we know alpha to be, it will commute, a dagger will commute with alpha. Only it will
Yes,
get,
yes, yes,
countable commutation will be.
exactly. Okay, good. So, therefore, what we have seen is that once you have this definition, which is trace of rho delta alpha star minus a dagger delta alpha minus a, then from there you can figure out your rho. Okay. And this is unique. Now, you see that this is kind of interesting. So, this is an operator, but this is normally ordered operator, because a dagger came first and then a. So, this is normally ordered. Right. Okay. Now, for calculation purpose, I will have to do little bit more, because as I said, like calculating this kind of thing is not so trivial. Okay. So, let me write down the expression for these operators, and then I will try to prove it. Okay. So, this operator alpha star minus A dagger times alpha minus A, this you can show that this is equal to 1 by pi square integral d square beta exponential of minus beta alpha star minus E dagger exponential of beta star alpha minus E. Okay. So, this is a representation of this delta function in terms of well behaved operators. Okay. Similarly, you can also show that this is not Gaussian, no, this is not Gaussian.
So, what expression for delta function did we use here?
What expression for delta function we are going to use? So, what I am going to prove that this is indeed equal to this by taking the expectation value with respect to any coherent state. Okay.
So, this equality how we got here.
That is what that is.
So, I just have to prove that.
Yes, yes, and it has an alternative expression which is nothing different, but we have to use it one or other interchangeably. Okay, minus I beta star alpha minus A. So, what is it that I have done? You replace this beta by iota beta, and that is possible because it does not change the integral. Okay. So, now this so, here we have seen that this is of course the definition of this p function. Given rho, you can find out the p function through this, although this is not a well behaved operator. So, we will have to look for some alternative, how to calculate things. Okay. This is definition fine. So, the question is, given rho, how to calculate this thing? This is of course definition, but as I said, this is not a well behaved operator. So, calculating this is not easy. Okay. So, for that what we can do is the following. So, we will prove this thing later, we will prove this thing, it is easy, we can prove it, we will prove that. Now, what you do is you take this expression, this we have proved, right. So, now what you do is take this matrix element. So, this is a peculiar matrix element, not beta beta, minus beta beta. Okay. And why this minus beta, it will become clear later. So, this is alpha belonging to C, d square alpha. So, from now onwards I will remove this prime, because I know that this is what we have considered earlier. Okay. Alpha alpha star minus beta alpha alpha beta. Now, maybe one of you should tell me what is the expression for this, what is this thing, minus beta alpha, this is exponential of minus half beta square plus alpha square and then there is some function. What was that?
minus alpha star beta or beta star alpha.
E to exponential
Okay, half of beta star alpha.
half of beta star alpha. One can calculate this thing, but minus of this. I mean, you will have to take basically this formula, e to the power minus mod alpha square by 2, n is equal to 0 to infinity, alpha to the power n by n factorial and n. So, if you use that, hopefully this is correct. This is correct, right? Okay, it looks okay. So, if I put that expression, what you will get is the following: e to the power minus beta square, because 1 beta square will come from here, half beta square will come from here also. So, e to the power minus beta square, then alpha belonging to C, d square alpha, and then this is p rho alpha alpha star times e to the power minus mod alpha square. Again it will come from here, 1 will come from here, minus half mod alpha square, and 1 will come from here, okay, times exponential of this is beta alpha star minus beta star alpha. Yes. So, you can use this expression and you will see that this is the case. So, in other words, if I take minus beta rho beta e to the power beta square, what I will get is this expression. Now, what is this? This is basically two dimensional Fourier transform of this function. I mean complex Fourier transform of this function, right? Okay, good. So, once you have the Fourier transform, so this is Fourier transform of this function. So, you can do the inverse Fourier transform to get p rho of alpha alpha star. Is that clear? I mean, if you have problem with complex Fourier transform, what you can do, you can write it in real and complex, real and imaginary parts, then things will be clear. Okay. So, you take inverse Fourier transform, I mean inverse Fourier transform of this, right. So, what you will get is, so this will provide you p rho alpha alpha star into e to the power minus mod alpha square, because that is the function you have obtained, is equal to 1 upon pi square, because when you do inverse Fourier transform you will have 1 upon pi square there. So, 1 upon pi square, then beta belonging to C d square beta minus beta rho beta e to the power beta square, then exponential of minus beta alpha star. So, it was yes plus beta star alpha, because just the negative of this one, this exponent, right. This is what you will get. Okay. So, if I take it here, it will be e to the power mod alpha square. So, you see that given your rho, you can figure out what is the p distribution function. Of course, this is what we have written here. This is our trace of rho delta alpha star minus a dagger delta alpha minus a, but this is more in a form which you can calculate, right. Okay. So, now maybe one or two example will tell you that now you can see that this is a bit a tricky issue, tricky in the sense that you have mod beta square here. So, this itself is a kind of diverging function. Okay. So, unless it is compensated by this part or by this part, okay. So, this function is not a well behaved function. But from the definition of this p rho, you can see that this is a real valued function. Why? Because if you take a complex conjugate of this, it will be it will be same as this, right. So, therefore, this is a real function. The other thing you can figure out is that alpha belonging to C d square alpha p rho alpha alpha star this is equal to 1. So, this you can prove, just take any definition, whether this definition or that definition, whatever be the case. So, this tells you that this is a this is a kind of quasi probability. Why quasi probability? Because this is not a well behaved function, this can shoot up, unlike probability distribution. In fact, this can also be negative, but this is real. Okay. So, this is for you to verify, or maybe I will do it later if I have time, I will do it later. So, maybe this part I will just erase this part, this I will do later. Okay.
Integral being 1 is like Parseval's inequality.
Parseval's, what is that Parseval's theorem? It tells you about the no, this is just normalization. It is nothing to do with the Parseval's one. Okay. I mean, for any probability distribution, this is the bare minimum you will have to satisfy. Okay. So, now what about the so if I take rho as a coherent state, we already told you that what will be the p function, but from here can you figure out that this is actually the delta function alpha minus beta. Can you actually figure out that? Or because I have used beta, so take gamma if you are, so take here gamma. So, this is I think for you, you can figure out this. Okay. So, this is your homework if you want. Right. Now, let us look at, okay, I will have to erase this part, I will come back to this later. So, generally for complex numbers, when people use this thing to say that this is 2-dimensional delta function, but that is okay. So, now let us take, this is important, let us take a thermal state. So, what you see is that for any coherent state is p distribution is a delta function, which is not a well behaved function, but still okay. It is non negative and all those things are there. So, let us take thermal state. So, for quantized radiation field, thermal state is something like this. So, you take the n is equal to 0 to infinity e to the power minus beta, h is here a dagger a plus half, okay, divided by trace of e to the power minus beta a dagger a plus half or 1. This is half, right, because half will be the correspondingly will be the vacuum energy, right. So, plus half, right, beta is the inverse temperature, and we know that so what is e to the power minus beta a dagger a plus half in terms of Fock states. This is sum over m is equal to 0 to infinity e to the power minus beta m plus half, then projection on m m. So, these are the Fock states, right, because this is a number operator and kth m is an eigenstate of this a dagger a with respect to the eigenvalue m, right. Okay. So, this I can write therefore as, oh no, this sum is not there, sorry, this sum, because this is on an operator, there is no sum. So, now, so therefore, from here if I look at trace of e to the power minus beta a dagger a plus half, what will I get? I will get m is equal to 0 to infinity e to the power minus beta m plus half, right, because this trace is 1. And what is this? This is e to the power minus beta by 2, then sum over m is equal to 0 to infinity e to the power minus beta to the power m. So, this is a geometric series. So, what will be this value? One by 1 minus e to the power minus beta, right. Is that correct? Okay. So, yeah, so this is fine, right. Okay, good. So, therefore, this will be sum over n is equal to 0 to infinity e to the power minus beta n plus half divided by, now I should be careful, maybe what I should do is I will take it on this side. So, this is e to the power beta by 2 e to the power minus beta by 2, yeah, 1 by this thing. Okay. So, what is that? Anyway, it is fine. So, this is 1 upon this. So, this into e to the power beta by 2 minus e to the power minus beta by 2 into n. Okay. So, now I will have to multiply by this. So, this is n is equal to 0 to infinity e to the power minus beta n, then this I can take outside. Okay. This I can take outside. So, e to the power minus beta by 2, if I multiply this, what will be that? 1 minus e to the power, so minus beta by 2 minus, so minus beta into n is equal to 0 to infinity e to the power minus beta n. So, this is my thermal state, right. Okay. Yeah. Okay, good. Now, yeah, so I should avoid this beta every time inverse temperature, because what is experimentally done is average photon number, not this temperature beta. So, what we need to look at is n is equal to 0 to infinity n times probability of getting this n. So, this is my average photon number, okay. So, which I denote by n bar, okay. And this is what we get in experiment, not the temperature. So, now you can tell me what will be this. So, what is your n rho thermal n from here?
1 minus e to the power minus beta times e to the power minus beta.
n, right? Okay. Yes. So, therefore, this is 1 minus e to the power minus beta sum over n is equal to 0 to infinity n e to the power minus beta n, right. And what is this quantity? This quantity. So, if you take derivative of sum over n is equal to 0 to infinity e to the power minus beta n, what will you get? So, you will have to minus 1 by beta, right, is not it? So, what will you get here? N e to the power minus beta n, right. Yeah, anyway. So, basically I need this expression. So, what is this quantity? So, this is equal to 1 by 1 minus e to the power beta, right. Yeah. So, anyway, so you can figure out what is the value of this. Okay. So, from there you replace beta in terms of n bar, because that is the quantity that you will get. So, what you should get here is maybe let me write like this. So, this is this n bar. So, n is equal to 0 to infinity, there will be some function, I mean sequence depending upon n bar, okay, as n n. So, simply what I have done, I have replaced beta by n bar, okay, not exactly replacing, I mean take the corresponding functional form, okay. Instead of beta you use this n bar. It has particular form, I forgot what will be the form, anyway you can figure out from there. So, this has, so find out what is this, you understood what is it that you need to look for, right. So, once you have this expression, put it there and then figure out n bar and then do the inverse transformation to express beta in terms of n bar, and that will do the job. Okay, good. So, now you have this rho thermal, yes, you have this rho thermal. Okay. So, now if I want to figure out P rho thermal, again when I write rho thermal it corresponds to the average photon number, right, because this n bar corresponds to the inverse temperature, therefore, average photon number. So, this will be e to the power, so this is alpha alpha star mod alpha square by pi square, then beta belong I am using beta again. So, maybe use gamma. So, d square gamma, here it is minus beta. Now, for rho thermal you will have to, yeah, you will have to use this rho thermal n bar beta e to the power, not beta, gamma. So, mod gamma square, then exponential of minus gamma alpha star plus gamma star alpha. So, basically you need to calculate this quantity, and how will you do that? You have this expression rho thermal, and if you take this, this is now simple, what will you get here. So, gamma rho thermal n bar gamma. So, you will have to look at this overlap of the Fock state with respect to coherent state, and that is very simple. Okay. So, you can figure out that. So, basically what will be the result, ultimate result. So, what you will see is that this is a Gaussian function of mod alpha square or mod alpha, sorry, it will look like something like that, one can figure out e to the power minus some factor times mod alpha square by some factor, something like this, okay, right. So, this is a Gaussian function, right. So, for thermal state p distribution function is a Gaussian function. So, it is a well behaved function, right, and as a result, as I told you last time, this tells you that thermal state is a classical state. Why? Because in this representation of rho d square alpha p rho alpha alpha star alpha alpha, because this is a, so this is a proper probability distribution for the thermal state. So, this will be basically then a mixture of these coherent states which are classical like states, and hence this is also a classical state. So, a thermal state is a classical state. Okay. Its p distribution is Gaussian and therefore, it is a classical state, and which is expected, like this thermal light, what we get to see is it is a it has of course, this is not a single mode, it is multi-mode case, and there is nothing non-classicality here. Okay, good. On the other hand, if you take, so this will be again a bit tricky, but you can in principle figure out what will be the p distribution for a photon number state, Fock state, right. So, what you will see is that this is a kind of something like this, some delta function, maybe alpha or something like this, and maybe alpha star and something like this. Okay. So, this also you can figure out from this relation, it is not difficult. I mean, just take here n, right. So, you see that for a Fock state, this p distribution function is highly singular, because this is nth derivative of delta function. Okay. So, this is highly singular function, and this is kind of expected, because Fock states, photon number states are very non-classical states. This we have seen last time also, when you take the expectation value of your quadrature observable with respect to a Fock state, it does not depend upon your theta. What is your, whatever be your theta, it is independent, it will give you the value 0, right, average value 0. So, it does not care what theta is there, what alpha is there, I mean sorry, yes. So, what angle you are doing, it is always 0, but so, and this is what is reflected here. Okay. And as I said that this p distribution is the only distribution which provides you all the possible information about non-classicality oblique classicality of your state in the yes of your state. Okay. Right. What is the time now? We still have time. Okay. So, so let me prove that part, and then I will come back to the Q distribution function. Yes. So, what I said is that delta of alpha star minus A dagger times delta of alpha minus A, this has this representation pi square beta belonging to C d square beta exponential of minus beta alpha star minus A dagger exponential of beta star alpha minus A. Okay. So, this is in terms of the OLBF function. So, how to do that? Because this is the expression we have used, right. So, let us take from this side so this is any coherent state gamma, right. So, this will be delta of alpha star minus gamma star delta of alpha minus gamma, right, and this of course it will be 1. Now, let us take this one 1 by pi square beta belonging to C d square beta gamma exponential of minus beta alpha star minus A dagger exponential of beta star alpha minus A gamma. Okay. So, what will I get? What about this part? So, this will be exponential of minus beta alpha star minus gamma star, and this will be exponential of beta star alpha minus gamma. Do you agree with me? Okay, right. And now, is easy integral, it is not so difficult. You can show that this is actually this one delta of alpha star minus gamma star delta of alpha minus gamma. Okay. So, yeah. So, in terms of coherent state basis, this is what you get to see. Now, you can say that look, I am not taking something like this, gamma and gamma prime. What about that? This is a kind of diagonal operator already. So, you do not have to look into this off diagonal one. You can do that, but that will not give you anything new. So, because this is true for any such coherent state, from here you can claim that this equality holds good.
So, we don't need to go for gamma prime.
Yes, because
Gamma
this
itself will
will work. Yes.
But why is that the case? Because if I find the diagonal elements, I'll still get non-zero, right? Like from the calculation on the LHS.
gamma is the whole complete set.
Sure, but gamma projected on gamma prime.
Yeah, you can do that. That is, I am not saying you cannot do. You can do that, but it will give you 0. If you take gamma and gamma prime unequal.
Yeah, that's what I'm not convinced.
Mm-hmm.
Because
They are not orthonormal.
yeah, they're not orthogonal. Maybe because of the delta function. Because delta
Yeah, it is because of delta function only. This is why I am telling. If it is not delta function, you will have to do it for all the basis elements. Okay.
yes.
Because delta function is already diagonal.
Yes, because delta has alpha star and alpha. So
Right.
if you have gamma and gamma prime which are different, then you'll just have
Exactly. Okay. So, in the same way you can prove the other expressions also, where I have used this, what is that, minus beta and this is I, this is simple, same thing we can prove. But one more thing is important is, and this is what we are going to use later. So, this is you can say that in our expression for P rho alpha star, which was trace of rho delta of alpha star minus A dagger delta of alpha minus A, right. So, this is normally ordered. Okay. In the same manner, you can define also these Q function which we defined earlier. So, this alpha star, so this is Husimi Q function. Husimi Q function So, this you can, so if you can show that this is rho delta of alpha minus alpha A delta of alpha star minus A dagger. So, this is anti-normally ordered. So, this is normally ordered, this is anti-normally ordered. Okay. And as we have shown that this is what the p distribution function is, you can show that this is your alpha rho alpha by pi, which we have discussed last time. Okay. So, this is your q distribution function. Okay. And once again, if you take some operator anti-normally ordered A is dagger, which is sum over n and m is equal to 0 to infinity d of n m, then A to the power n A dagger to the power m. So, this is anti-normally ordered. Then if you take trace of rho O A dagger, you can express it as earlier, alpha belonging to C d square alpha q of rho alpha alpha star, which is the distribution function, times the corresponding functional form. And what is this? This is just replace A by alpha, A dagger by alpha star. Okay. So, this is what we do like in classical statistical mechanics, right. So, this is what I mentioned in the beginning, that q function comes from the anti-normal ordering of operators, p function comes from normal ordering of the operators. We will discuss next time about the Wigner function, which comes from the symmetric ordering, where you do not give any preference to A powers of A or powers of A dagger. Okay. So, from there you will get, from symmetric ordering you will get Wigner function, and which is a well behaved distribution function. Of course, not probability distribution, because it can be negative, but it is bounded. As I told you, this is a, this q function is, although it is a kind of probability distribution function, it is a probability distribution function, but it does not capture non classicality of states. Okay. Yes.
When we are calculating expectation,
Yes.
Then the Rossini Q function and P distribution functions both are giving the same results. I mean, in the way we have defined it. Trace of rho.
No, this is not same as, even if you take the coefficients for this and this to be same, these are not same.
I mean, we can go from one to the other.
Yes, that you can go, that you can go. So, this connection is there. I'll so from P to Q, Q to P we can go. I mean, from Q to P it is easy. So, you express this rho in terms of P distribution function. So, then you can express Q as an integral of P function.
I was saying that OA and ON,
Yes.
We can go from one to the other.
Yes.
So, I mean, suppose we have some observable in terms of normal ordering, we can go to.
Yeah, you can go
and
from. You
so
can,
the expectation will.
no, my point is you can go from here to its to its normally ordered form. That is fine. That will give you, of course, the same expectation value, same value. But the point is, this is important, that there, as we discussed last time, I mean earlier. So, let us say that OA A dagger, which is n and m is equal to 0 to infinity d n m A to the power n A dagger to the power m, right. Let us say that this is equal to n m is equal to 0 to infinity C of n m A to the power A dagger to the power n A to the power m, right. I mean, this one can always do that from here to here. Okay. So, now if I look at trace of rho O A dagger, Of course, this will be same as res of rho. So, this you can call as well, I do not want to call it as same O, maybe O prime of n A and A dagger, right. Okay. So, this is of course same as O n prime A dagger, no doubt of it. Now, this you can express it as d square alpha, this is q function of alpha alpha star, then O A alpha alpha star. This you can express as alpha belonging to C d square alpha p rho of alpha alpha star. See, this does not depend upon what operator you have chosen, this depends only upon rho, and then this is O prime n alpha alpha star. Okay. So, how will you get this? Just replace A by alpha, A dagger by alpha star. How will you get this? Just replace A by alpha, A dagger by alpha star. That is it. These two are of course same.
So, when we observe some quantities, so how will know that that is, I mean, just as you said that Q of rho doesn't say about the quantum nature of the photons.
Yes, yes,
so how
yes.
will know by detecting some photons that
Yeah. So, the question is, what is it that you are going to address? If you want to address non-classical nature of your light source, one-term light source, P function is not good function. You can use that, but you have to go back to the P distribution, etc. So, for that you should go to P distribution or your linear distribution. So, it depends what is it that you are going to address. So, it is like in quantum theory we have different pictures, right? Schrodinger picture, Heisenberg picture, interaction picture, it is like that. Average value anyway it will be fixed.
So, in a way that if we want to see the evolution of the state, then we will have to go to the P.
Not necessarily. If you want to look at the evolution, okay, so you are talking about time evolution, right?
Yeah.
So you can take P, you can take linear distribution, you can take Mussini. I mean, linear distribution is more appropriate, I would say, to look at the evolution, because that is very close to the corresponding classical what is happening in the classical dynamics. It is more easier.
But we need to see the quantum nature.
So when you look at quantum nature, see, dynamics wise, this is the tricky issue. If I look at dynamics of a physical system, how do you figure out whether there is something non-classical in that dynamics? So if you look at the dynamics of a system, physical system, whether it is classical or quantum, for closed system, classical system, I have the Hamiltonian description, right, phase space description. For quantum system, I have the Schrodinger evolution. But by just looking at the Hamiltonian of a classical system versus quantum system, can I figure out that this is a quantum system or this is a classical system? No, right? Because what is it that you have done? You have just lifted the corresponding, because you have knowledge about the classical system, you have lifted it to the corresponding quantum system. So, at a dynamics level, it is difficult to figure out whether your system behaves classically or quantum mechanically. I am not saying it is impossible, but generically it is difficult. So, what we look at a time instant. So, we look at the kinematics. So, I take a photograph or a time stamp statistics, and from there I figure out whether it is classical or quantum. I mean, dynamics also one can look at, but those are much more tricky issue. You will have to look at some non-linear gadgets and all that. Okay, good. So, any other question?
What textbook are you like this? What textbook do you suggest for this course?
So, I will follow mostly this. So, I told you about the two papers, right. Prem, can you forward that paper to you? No, he is new. I think you can ask from Prem. This is Cahill and Glauber. They have two papers in, I think, 70s, in both in Physical Review A, right. Yeah. So, I am following this book by Scully and Zubairi. This is quantum optics. So, I will follow this one. This is the book. Sometimes I will follow these two papers, this Cahill and Glauber. I think this is PRA 1970s, maybe 19. So, I think 77, right, Prem, or 79, something like that. Yeah, there are two volume paper. Huh?
Both, no, sorry, 69.
Oh, sorry, 69. Yeah. There is also another book which is, I mean, I like it very much. You may not like it. So, this is written by two experimentalists. Okay. Again, I remember only one of the authors, Timothy Ralph. This is something like an experimentalist approach to understand quantum optics. Okay. This may not be the exact title, but Ralph has written only one book. Okay. Timothy Ralph, this is a 2004 book, but it has a 2019 edition also. Okay. Ralph and another person. Okay. So, this is like an experimental guide to quantum optics or something like that. Okay.
A guide to experiments in quantum optics.
Right.
Hans A.
Becker. Okay. And Timothy Ralph, right. Yeah. So, this book I like because it has given some experimental idea how to understand this classicality, non-classicality, but it's up to you.